Let's investigate the connection between Poisson brackets in classical mechanics and commutators in quantum mechanics. First, let's have a look at the Lagrangian and Hamiltonian formalisms in classical mechanics. We're going to be building abstractions on top of each other. So one of the most tangible ways to look at classical mechanics is through Newtonian mechanics. Forces and Newton's laws of motion, they are very tangible. You can feel forces. But what we're going to do is we're going to generalize these concepts from classical mechanics, and we're going to turn them into abstractions. And we're not going to be able to touch things like the Lagrangian or the Hamiltonian, but they will be useful mathematical tools for describing physical systems. One of the most fundamental principles in classical mechanics, and also in all of physics, is an action principle, and specifically a stationary action principle. And from that principle, we can derive the Euler-Lagrange equations. And I'm going to write down the Euler-Lagrange equation for a very general sort of system. So first, I'm going to have a time derivative. So this is a derivative with respect to t. T is time. And I'm going to differentiate a partial derivative of the Lagrangian with respect to something that plays the role of a velocity. And that's q dot. And I'll talk more about q in a moment. So I'm going to put a little subscript I down here, because it's not the only q that exists. There could be other q's. And we're going to go into more details after I write down some important expressions. So let me close this bracket over here. This set of derivatives over here is equal to the partial derivative of the Lagrangian with respect to q by itself. So over here we have a dot, and over here we don't have a dot. And that comes from Newton's notation for time derivatives. So putting a dot above a variable is shorthand notation for taking the time derivative. It's the same as this combination over here, taking the time derivative. And it helps to simplify a lot of notation. So this is known as the Euler-Lagrange equation. So Euler and Lagrange were two very famous mathematicians. And you can derive this from the stationary action principle. Now this actually generalizes to field theories as well. But what we're talking about are coordinates, q. So q are these generalized versions of coordinates. In Newtonian mechanics, we're used to dealing with coordinates like x, y, and z. Those are the Cartesian coordinates for 3 dimensions. We also have different types of coordinate systems in Newtonian mechanics. You can switch to polar coordinates. And in 3 dimensions, you can use spherical coordinates or cylindrical coordinates. There are a lot of different types of coordinate systems. But what this q is denoting is a general coordinate. So it could be x, y, z, or it could be something else. It doesn't even have to have the same units as the coordinates that we're used to from Newtonian mechanics. It doesn't have to have units of position, which are units of length. And we'll see that in the next video as well. So this is a very fundamental equation called the Euler-Lagrange equation in Lagrangian mechanics. It is actually the equivalent of F equals ma. So in Newtonian mechanics, we have F equals ma. We link the acceleration of some particle to the sum of all the forces acting on that particle. And then we can generalize that from particles to bodies. You can think of rigid bodies. And it's a very fundamental concept. And it links together a lot of these fundamental quantities. And another observation you can make about F equals ma is that it is a second order differential equation. Acceleration is the second time derivative of position. Over here, we also have a second order differential equation. You can see that we have one derivative acting on this Lagrangian, and then we have another derivative. So when we substitute in the Lagrangian into this equation, we will get the equations of motion. And in general, there's going to be an equation of motion for each of these indices, I. So I is just the index for which coordinate we're dealing with. So that is the Lagrangian formalism. And it all comes from the stationary action principle. We impose that principle. We say that the universe chooses trajectories such that the action is stationary. And by stationary, I mean it could be a minimum, it could be a maximum, or it could be a saddle point. Because in general, that action is going to depend on many, many variables. So in multivariable calculus, you don't just have minima and maxima, you also have saddle points. In the special case where we're not just dealing with the stationary action principle, but we're dealing with the principle of least action. That is the case where we're dealing with a minimum. That's where the trajectory actually minimizes the action. So I just want you to be aware that this comes from the stationary action principle. And in general, you can have more complicated relationships, especially when the Lagrangian depends on higher derivatives, higher order derivatives of this coordinate. And the Lagrangian in general could also depend on time. But this is a nice, simple, and concise Euler-Lagrange equation. And we will be using that in Lagrangian mechanics. Now let's move over from the Lagrangian formalism to the Hamiltonian formalism. And the Hamiltonian formalism uses a lot of the same type of language as the Lagrangian formalism, but it's a little bit different. So I'm going to write down a transformation that's going to take us from the Lagrangian to the Hamiltonian. This H over here, capital H, denotes the Hamiltonian. And we're very familiar with the Hamiltonian in quantum mechanics because this language of Hamiltonians translates from classical mechanics to quantum mechanics. This function, H over here, actually depends on the q's, which are the coordinates. So I'll write q sub I. And it also depends on p's. And p's are momenta. So we don't have q dot over here. We have p in place of q dot. And I'll talk a bit more about that when I write this transformation. So this Hamiltonian, which depends on coordinates and momenta, which are indexed by I, that is equal to the Legendre transformation of the Lagrangian. So I'll write down this Legendre transformation. And it's a very general transformation. So I'll write a big sum over here. And this is a sum over all these indices. I'm going to have momentum over here. And I'm also going to have q dot. So q dot plays the role of velocity. And this plays the role of momentum. And I'll put an index I underneath these guys over here. So that's a little subscript I. And that's saying that in general, we don't just have one coordinate and one momentum, we could have many. So this could be a multi-dimensional system that needs many coordinates to describe it. But we're talking about a discrete number of coordinates. This is a discrete number of coordinates, and it's a finite number of coordinates. If it wasn't discrete, then this sum would have to turn into an integral, because summation turns to integration when we turn the discrete into continuous. Now, this is not the complete Legendre transformation. We have to subtract off the Lagrangian. And this is an L. It's a slightly fancy L. The Lagrangian depends on the q's, so q sub I, and the q dots. The q dots, remember that dot notation is just for time derivatives. So this is a very fundamental relationship. And so is this one over here. This is the fundamental relationship for Lagrangian mechanics, and this takes us from Lagrangian mechanics into Hamiltonian mechanics. And what about the equations of motion? How do quantities change in Hamiltonian mechanics? Well, we no longer have this second order differential equation given by the Euler-Lagrange equation. Now we have two first order equations, and they're called Hamilton's equations. And I'll write them over here. If we want to find out how the q's are changing, so q sub I, if we want to find the time derivative of each of these guys, well, we have to take the derivative of this Hamiltonian with respect to the momentum. So I'll write this down over here. We have h, and down here we have p sub I. So this is one of Hamilton's equations. Now I'll write another one over here, change colors so this is very clear. If we have momentum, which is indexed by I, and we want to find the time derivative of that momentum, that's equal to an analogous expression, except there's a minus sign. We have minus the partial derivative of the Hamiltonian with respect to q. And this index I tells us that this is valid and holds for all of the i's, for all of the different coordinates and for all of the different momenta. So can you see what we've done in going from Lagrangian mechanics to Hamiltonian mechanics? In Lagrangian mechanics, we have this second order differential equation, and that is the equation of motion. But then when we take the Legendre transform and we go from the Lagrangian to the Hamiltonian, we have translated this function, which depends on q's and q dots, to a function that depends on q's and p's. And now with this, we can define Hamilton's equations, and they are both first order differential equations. And that's often something you use when you're solving second order differential equations, or in general, any higher order differential equations. you want to split that up into more manageable equations that have a lower degree of differentiation. So if you have third order derivatives or fourth order derivatives, you want to define new variables. You want to split that up into equations that are easier to solve. And that's essentially what we've done over here. We've taken a second order differential equation and we've turned it into two linear first order differential equations. So over here we have the Hamiltonian and over here we have the Lagrangian. And these are called Hamilton's equations and this is called the Euler-Lagrange equation. So have a look at this transformation, the Legendre transformation. If you're familiar with some of the concepts from thermodynamics, then you will have encountered Legendre transformations there as well. That's anytime we want to deal with a different sort of potential energy function, and we want to express it in a different set of variables that are more convenient. Lagrangian mechanics works very well with coordinates and velocities, and these velocities are the time derivatives of coordinates. But there is a very special relationship between coordinates and momenta. And that is present in Hamiltonian mechanics. That's why the Hamiltonians are written in terms of the Q's and the P's. But in general, the P's don't have to have units of momentum. They don't even have to be momentum. They just have to behave like momentum in Newtonian mechanics. So they're sometimes called the canonically conjugate variables. So you use these Q's to get the P's. And how do you find the P's if you know the Lagrangian? Well, if you look inside the Euler-Lagrange equation, this term in the bracket, that is actually the canonically conjugate momentum. So differentiating the Lagrangian with respect to q dot, that gives you this p. So instead of p over here, I could have written this partial derivative inside here. And that would, again, be summed over. So this is taking the Legendre transformation for each of these indices, and it's turning this equation, which has q's and q dots, into an equation that has q's and p's. Now, what I want to do is introduce the Poisson bracket. So we're layering these abstractions on top of each other. We've gone from the tangible world of Newtonian mechanics to the Lagrangian formalism, and then from the Lagrangian formalism, we've taken the Legendre transform to the Hamiltonian formalism, and now we can use Poisson brackets. And that's going to reveal some very fundamental properties between position and momentum. And those translate into quantum mechanics as well. So I'll write this underneath here. Let's say we have the time derivative of some function. I'll call that function f. And f depends on some q's, depends on p's, and let's put in, this is an I, let's put in an explicit time dependence as well. So it depends on the coordinates, which are the q's, it depends on all the momenta, and it also depends on time. There is an explicit time dependence. A lot of the time there's an implicit time dependence. You can depend on time through other variables, right? If you depend on position and velocity, then indirectly you depend on time. But if you also have an explicit time dependence, then we write that like this. So this is just a function of all the q's, p's, and t's. Now I could write out q1, q2, q3, q4, but that is a very clunky and messy notation. That's why this index I is used. So we have qi and pi. Now, what is this going to be equal to? We can use the chain rule. We can use the chain rule and we can write this as a big sum. So we're going to have a big sum, again, over the index I. And what's going to be in this sum? Well, we know it depends on q, and we know it depends on p. So there's going to be terms from the chain rule involving derivatives with respect to q and p. So I'll write them over here. We're going to have partial derivatives with respect to f, partial derivatives of f with respect to all of the q's. So I have qi. And then, because it's the chain rule, we're going to need a time derivative of q. So we have the q dots. And we're going to have to add to that the partial derivative of f with respect to the p's. So I have p sub I. And again, we need a p dot over here. And I'll close this bracket. So this is just using the chain rule, right? This dot notation is just shorthand for dq dt. And this is dp dt. So we're just taking the time derivative. Now this is application of the chain rule when you have many, many variables over here. So you have an index for all the variables. But this is not it. We still have an explicit time dependence. So let's put the explicit time dependence over here. We have the partial derivative of f with respect to time. So you could also put t dot over here, but t dot is dt dt, and that's just equal to 1. So what do we have over here? We have all of the variables that this depends on. We've broken it up using the chain rule. But do you notice that there's a q dot over here and a p dot over here? We know from Hamiltonian dynamics that Hamilton's equations apply. So we can substitute this and this in here. And I'll do that. I'll do that over here. So what we're going to get is, we're still going to have this big messy summation, but it's going to turn into something that is very familiar. So what's going to happen over here? We're going to have df dqi, so df dqi, and what is q dot going to turn into? Well, that's this one of Hamilton's equations. We're going to have dh dpi, and what's going to happen to this term? Well, p dot has a minus sign. So it's going to introduce a minus sign, and then we're going to have dh dq. So we're going to have minus df, and what are we differentiating with respect to? We have momentum here first. So this is pi down here. And then we have this q derivative. So we have the Hamiltonian differentiated with respect to q. And I'm keeping track of all of these indices as well. I'll close this bracket, and we can't forget that explicit time dependence. So we have a partial derivative with respect to time. This partial derivative is not the same as this total derivative. Over here we have a total derivative. It's written with the normal d's. But everywhere where we have a curly derivative, that is a partial derivative. So this is a partial derivative, and that only takes into account that explicit time dependence. Whereas this total derivative takes into account all of the ways that this function can depend on time. This function depends on time through q, and it also depends on time through p. And it also has that additional explicit time dependence. Have a look at what we've just shown here. So by substituting in Hamilton's equations from Hamiltonian dynamics, we've shown that this q dot and this p dot introduce these terms. And one of these terms has a minus sign. Have a look at what is being differentiated with respect to. We have a q and a p, and then we have a p and then a q. And we have a minus sign. This structure is actually the Poisson bracket, where we're swapping things around. And this kind of behavior where we're swapping stuff around and then taking the difference, that is present in quantum mechanics as well. So this is analogous to the commutator in quantum mechanics. And I'll write this down in a far more condensed form. Let's take the condensed notation of f dot. So this is the same as what we have up here, f dot. And I'm not going to write out all of these dependencies over here. So this f still depends on all the q's and all the p's, and it has an explicit time dependence as well. So this is the total derivative of f. And that is equal to the Poisson bracket of f with the Hamiltonian plus this explicit time dependence, partial f with respect to time. So this is a condensed way of writing all of this. These curly brackets with a comma over here, that is read as Poisson bracket of f with h. And this is condensed notation for this massive summation over here. So what if you only had one coordinate? Then you'd only have one canonically conjugate momentum. So you'd only have one q and one p. This sum would disappear, and you'd just be left with this swapping of derivatives around. And that's what's going to happen if we have one-dimensional problems, where there's just one coordinate. And we'll see that in the next video. So this is what I'm calling the Poisson bracket. And this, in general, is the time dependence for any function of q's, p's, and t's. Let's have a look at a special case of this equation over here. What if this function was one of the q's? What if we took one of the q's? So if we take one of the q's, we have q dot, and it's one of the specific q's, so qi, that's what we're looking at. We're looking at the time derivative of this q. What is that going to be equal to? Well, let's have a look at the Poisson bracket. We're going to have the Poisson bracket of qi with the Hamiltonian. And are we going to have anything over here? No, because this does not have any explicit time dependence. It only depends on q. So the function is just one of the q's. And what is this equal to? Well, if we go back to the Poisson bracket, we are only focused on one of these indices. So let's have a look at what happens if we put q in place of f. This first term is going to have a derivative of q with respect to q. That's just going to give 1. But this term is going to have a derivative of q with respect to p. And q and p, those are independent variables. So these guys are all going to give 0. So everything over here is going to give 0. So we're not going to have any contributions from this term. And the only contribution we're going to get from this is when the index is the same. Because if you have another q, if you have, for example, qj, the derivative of that q with respect to that different q is going to be 0. Those are independent q's. They're independent coordinates. So we're only going to get one contribution that corresponds to the same index. And that contribution is going to be this. It's going to be the partial derivative of the Hamiltonian with respect to the momentum. And that is Hamilton's equation. We just recovered Hamilton's equation. That's this one over here. The partial derivative of h with respect to p. Now let's have a look at the other case for momentum. Let's put momentum as our function. So if we have momentum, and we take the time derivative of that, that's going to be the Poisson bracket of pi with the Hamiltonian. And that's going to be equal to, let's have a look at what happens. So again, there's no explicit time dependence. This function only depends on pi. The function is just pi. So if we substitute pi in place of f, what are we going to get? Well, this term is going to have a momentum differentiated with respect to a coordinate. And those are independent variables. So that's just going to give 0. This is all 0. So no contributions from this first term. That's the opposite of what we had when we were taking the Poisson bracket of q with h. So this disappears, and this is going to have a derivative of p with respect to p. And that's only going to give a contribution if the indices are the same. So we're going to get minus the derivative of the Hamiltonian with respect to q. And this is specifically the same index that we're talking about over here. So now we've recovered both of Hamilton's equations. Here we have this one of Hamilton's equations, and here we have this one of Hamilton's equations. So this derivative of p is given by this partial derivative with respect to q. And there's a minus sign. So there's almost a symmetry between q's and p's. But it's not a perfect symmetry because of this pesky minus sign. But that pesky minus sign is actually very useful because it allows us to define this Poisson bracket. So here we've seen that Poisson brackets can describe time evolution. And specifically, if we take the Poisson bracket with the Hamiltonian, we get time evolution. There's a very similar concept in quantum mechanics. I'll write that concept down here. If we take the time derivative of the expectation value of some operator in quantum mechanics, and I'm putting a hat on top of this operator A to make sure that this is an operator. This is not a classical function, right? All of these values up here, they're all classical values. But now what we're dealing with is an operator. It has a hat on top. So this is quantum mechanics. So if we take the time derivative of the expectation value of an operator, that is equal to, there's a factor of 1 over I h bar, and then we have an expectation value of the commutator of that operator with the Hamiltonian. But we also have an additional term. If there is an explicit time dependence, then we have to take the partial derivative of that operator with respect to time, and we also have to take the expectation value of that. This is called Ehrenfest's theorem, or in fact, it's a generalization of Ehrenfest's theorem. Ehrenfest wrote down this theorem specifically for position and momentum, and he recovered Newtonian mechanics. So what Ehrenfest did with this theorem is he saw that the expectation values in quantum mechanics behaved just like the quantities in Newtonian mechanics. So position and momentum, if you turn them into expectation values, well, you can go into the language of quantum mechanics. Or if you think about it, if you're dealing with the quantum formalism and you take the classical limit as all of those wave functions turn into spikes, then you're just going to get those wave functions represented by the expectation values. So classical objects have wave functions that are spikes, and they behave just like the expectation values. Or in other words, the dispersion or the variance of those wave functions is very, very small. So you don't notice the effects of quantum mechanics at the classical scale. That's why Newtonian mechanics is such a good approximation, and you wouldn't use quantum mechanics to describe balls flying through the air or projectile motion. So let's have a look at some of the similarities that we see with this expression from Ehrenfest's theorem, which was actually, this was written down by Heisenberg. This is in the Heisenberg picture of quantum mechanics. So over here we have something that looks like the Poisson bracket. Over here we have a time derivative of a quantity, and it's equal to some kind of commutator slash Poisson bracket plus some kind of explicit time dependence, which is taken care of by this partial derivative. So this form translates roughly. But there's a missing factor over here. We have IH bar appearing over here. We have to account for this factor. And it turns out that this is something that Dirac noticed. If you map from Poisson brackets to commutators, you have to introduce this factor of IH bar. Let me write down some very essential properties for Poisson brackets. And I want you to see that they have analogous properties in quantum mechanics as well. If we take the Poisson bracket of some of these Q's, so I have Qi, with a momentum, Pj, so this doesn't have to be the same index, so Qi and Pj, that is equal to the Kronecker delta symbol. So this is only equal to 1 if the indices are equal. Otherwise, the Poisson bracket is 0. Now let's have a look at the analogous form in quantum mechanics. So in quantum mechanics, if I take the commutator of these guys, so I have Qi and Pj, and I'm putting a hat on top, this is telling me that it's a commutator, this is equal to IH bar times the Kronecker delta symbol. And you can also implicitly write the identity operator here. And the identity operator is the operator which, if you take it and you act on with it on a state, it's not going to change the state. It's the unit operator or the identity operator. And what I also want to do is let me explicitly write out the definition of a commutator. So this commutator over here, this is saying, so this is the notation for a commutator. So we have A and H. This is equal to AH minus HA. And I'll put these guys on top over here. These guys are all hats. So this is the commutator in quantum mechanics. It has an analogous form to this Poisson bracket. We're swapping things around. Another very, very important thing is, if you take the Poisson bracket of Q's with other Q's, so we have Qi and Qj, that's equal to 0. And it's the same for the P's. If you have Pi and Pj, that's also equal to 0. And we can translate that in the language of commutators. If we take the commutator of Qi with Qj, that's equal to 0. And that's also equal to the momentum commutator. So we have Pi and Pj. And notice how I'm putting hats on all of these ones because I want to distinguish them from the classical versions. So this is the classical version, and this is the quantum mechanical version. The important takeaway message is that you can translate from Poisson brackets to commutators by introducing this IH bar. But it's not as simple as that. You have to turn these guys into operators. And operators are denoted by this little hat on top. So this I and this J, those are just separate indices. So they don't have to be the same I, they don't have to be the same Q's and the same P's. They can be different Q's and different P's. And this Kronecker delta symbol is just a condensed way of writing zeros and ones. Otherwise, we would have to define a piecewise function. And that's what this condensed notation is used for. So we've looked at the Lagrangian formalism, the Hamiltonian formalism. We've introduced Poisson brackets. We've seen how Poisson brackets describe the time evolution. And we recovered Hamilton's equations of motion from these Poisson brackets. We looked at Ehrenfest's theorem and Heisenberg's generalization of Ehrenfest's theorem in the Heisenberg picture of quantum mechanics. We defined the commutator of an operator with the Hamiltonian, and then we looked at some of these essential properties of Poisson brackets. And what you can do is you can transform the Q's and P's into other Q's and P's. And that's called a canonical transformation. And sometimes you can transform it into a more convenient coordinate system. As long as these properties are present for that transformation, you can call it a canonical transformation. That's a very essential topic in Hamiltonian dynamics. And that language of Hamiltonian dynamics translates into the language of quantum mechanics. And that's why we have these essential commutation relations. These Q's could be X, Y, Z, and these P's could be PX, PY, and PZ. So these are the fundamental commutation relations, and we've used them in a lot of the previous videos to derive a lot of relationships. In the next video, I'm going to have a look at an example of Lagrangian and Hamiltonian mechanics. So make sure you check out that video. You can find that in the Quantum Mechanics playlist if you click over here.